Picture this. You are standing on the rust-colored soil of Mars, under a thin pink sky, looking out across a landscape that is both utterly alien and strangely familiar. The air is silent, the horizon stretches into forever, and above you, the sun casts a weaker, colder light than the one we know on Earth. It's a scene that has captured human imagination for generations, a symbol of the next great leap for our species. But what if the key to thriving in this harsh new world isn't found in building upward toward that alien sky, but in digging downward into the very ground beneath your feet? And what if the wisdom we need to do it successfully isn't something we've just invented, but something we inherited, lessons carved in stone and soil thousands of years ago by civilizations who mastered the art of living beneath the surface? This is the story of how ancient tunneling techniques are inspiring the next chapter of human exploration. It's a tale that stretches from the underground aqueducts of ancient Persia to the labyrinthine cities hidden deep within the rocks of Turkey, and now to the ambitious plans for subsurface habitats on Mars. For millennia, humans have been going underground to seek shelter, to find resources, to hide from danger, and to build communities that could endure. They did it with simple tools, profound ingenuity, and a deep understanding of the Earth, qualities we will desperately need as we venture onto other worlds. In this video, we're going to journey through time and space, uncovering the brilliant methods our ancestors used to carve stability and safety out of the ground, and exploring how these age-old strategies are being reimagined for humanity's future on Mars. We'll see why going beneath the surface isn't just a practical solution to the planet's extreme conditions. It's perhaps the most poetic fusion of past and future ever conceived. So settle in and open your mind to the possibility that the secrets to building among the stars have been buried right here on Earth all along, waiting for us to dig them up. To understand where we might be going, we must first look back to one of the most enduring examples of human ingenuity, born from necessity in the arid landscapes of ancient Persia. Over 3,000 years ago, in what is now Iran, communities faced a relentless challenge: how to survive and thrive in a harsh, water-scarce environment. Their solution was nothing short of architectural genius, the Qanat system. This wasn't just a simple well, it was a sprawling, subterranean network of gently sloping tunnels designed to tap into groundwater trapped deep within the foothills of mountains and transport it over vast distances to the surface, purely using the unerring force of gravity. The construction of a single Qanat was a monumental community effort, often taking generations to complete. Workers, known as muqani, began by sinking a series of vertical shafts down to the water table, sometimes reaching depths of over 50 meters. From the bottom of the first shaft, they would then begin the painstaking work of digging a horizontal tunnel backward toward the base of the mountain, using hand tools like picks and hoes. The excavated material was hauled up through the vertical shafts, which also served another critical purpose. They provided vital ventilation for the diggers below and allowed for ongoing maintenance of the entire tunnel system once it was operational. The precision required was astounding. The slope of the main tunnel had to be calculated perfectly, just steep enough to keep the water flowing steadily, but gentle enough to prevent erosion that would cause the tunnel to collapse. A miscalculation of even a single degree over kilometers of digging could render the entire project useless. This mastery over hydrology and geology is what truly stuns modern engineers. These ancient builders possessed a profound, intuitive understanding of the land. They knew how to read the terrain to locate the most reliable aquifers and how to structure their tunnels to withstand the immense pressure of the earth above them. They lined the tunnels with ceramic rings or stone in unstable areas, creating a durable conduit that prevented collapse and minimized water loss through seepage. The result was a sustainable, low-energy water delivery system that could support entire cities and transform deserts into lush, agricultural oases, all without a single pump or any external power source. As Dr. Emily Carter, a historian specializing in ancient technology, points out, these were not crude holes in the ground. They were feats of precision and long-term planning that demonstrate a level of endurance and foresight we are only now beginning to fully appreciate with our modern tools. The legacy of the Qanat is a powerful testament to the fact that innovation is not solely the domain of the modern era. Our ancestors developed sophisticated, elegant solutions to existential problems, and they did so by working in harmony with their environment rather than attempting to dominate it. They built for permanence and community benefit, creating infrastructures that functioned for centuries. This is the exact mindset we need to carry with us as we look toward Mars. The red planet presents a set of extreme environmental challenges that echo the harsh, isolating conditions of ancient deserts. The Qanat teaches us that survival in such a place isn't about imposing our will with brute force and complex machinery alone. It's about careful observation, intelligent design, and creating systems that are inherently sustainable and resilient. It forces us to ask a profound question. If they could achieve so much with so little, what other forgotten wisdom lies buried in our past, waiting to be rediscovered and adapted for our future among the stars? So the question becomes, if building on the surface of Mars is such a monumental challenge, where do we possibly begin? The answer, it turns out, is not to build up but to build down. The surface of Mars is an incredibly hostile environment, presenting a trio of formidable obstacles that make traditional above-ground construction a perilous endeavor. First, and perhaps most dangerously, is the issue of radiation. Unlike Earth, Mars lacks a strong global magnetic field and has a very thin atmosphere, which means its surface is bombarded by intense solar radiation and galactic cosmic rays. This isn't just a sunburn risk. This is a constant, invisible shower of high-energy particles that can damage human DNA, significantly increasing the risks of cancer and other health problems over time. A settler living on the surface would be exposed to radiation levels hundreds of times higher than what we experience on Earth. Compounding this radiation threat are the planet's wild temperature fluctuations. A single day on Mars can see the thermometer swing from a relatively balmy 70 degrees Fahrenheit near the equator down to a bone-shattering negative 195 degrees Fahrenheit at night. These aren't just uncomfortable conditions. They represent an immense engineering challenge for any habitat's life support and insulation systems, requiring massive amounts of energy just to maintain a stable, livable interior climate. And then there are the dust storms. Martian storms are not like gentle winds on Earth. They can engulf the entire planet, lasting for months on end, blotting out the sun with fine, abrasive dust that would coat solar panels, jam machinery, and make any external maintenance a nightmare. Faced with this trifecta of radiation, temperature extremes, and dust, the most logical solution is to use the planet itself as a shield. By building our habitats underground, we leverage the most abundant local resource, Martian soil, or regolith, to create a natural barrier. Studies from NASA and other space agencies have shown that just a few meters of regolith overhead can reduce harmful radiation exposure by over 80%, bringing it down to levels much closer to what we consider safe on Earth. This same layer of dirt also provides superb thermal insulation, smoothing out those drastic temperature swings and creating a much more stable environment that requires far less energy to heat or cool. An underground habitat is also inherently protected from those planet-encircling dust storms, micrometeorite impacts, and the general harshness of the surface. This isn't just a theoretical idea, it's a survival strategy born from stark necessity. It fundamentally shifts the problem from how we shield a habitat to how we build one within the ground itself. And this is where the story loops back to our ancient predecessors, modern engineers confronted with the need to excavate and stabilize tunnels on another world, are realizing that transporting massive, heavy digging equipment from Earth is incredibly costly and inefficient. This practical constraint is driving them to look back at historical methods that prioritized cleverness over brute force, adaptability over power, and working in harmony with the local environment. The challenges of Mars are forcing us to reconsider what true innovation looks like, and in doing so, we are rediscovering the profound wisdom buried in our own past. So we've established that going underground is our best bet for surviving on Mars, protected from radiation and the harsh surface conditions. But this raises a monumental, practical question. How do we actually dig these tunnels and carve out these habitats on another world? To find the answer, we need to look at two very different toolboxes, one filled with the roaring, powerful machinery of the 21st century, and the other holding the simple, elegant hand tools of antiquity. On one side, we have our modern marvels, autonomous robotic excavators that can chew through rock with relentless efficiency, guided by laser sensors and complex algorithms. These machines represent the pinnacle of power and speed, capable of moving mountains of material with minimal human oversight. They are the logical extension of our industrial mindset, where bigger and faster often means better. But then we look back at the methods used by ancient Roman miners, for example, and we see an entirely different philosophy at work. These engineers didn't have diesel engines or hydraulic pistons. They had fire, water, and an intimate, hard-won knowledge of the rock itself. They used a technique called fire setting. They would build a blazing hot fire directly against the rock face they wanted to break. The intense heat would cause the stone to expand and develop microscopic fractures. Then they would rapidly douse the superheated rock with water or vinegar, causing it to contract suddenly and shatter. It was a process that required patience, a deep understanding of material properties, and very little in the way of complex machinery. The energy input was minimal, just some wood for the fire and some water, but the effectiveness was proven over centuries of successful mining. This is the core of the contrast. Modern machinery offers incredible brute force, but it often comes with a massive cost in energy, complexity, and weight. Transporting a giant tunnel boring machine to Mars is a logistical nightmare, consuming an enormous amount of precious payload capacity on a rocket. Every kilogram we launch costs tens of thousands of dollars, and once it's there, that machine would require a significant and constant power supply to operate, adding another layer of infrastructure we'd have to establish. Ancient techniques, by comparison, are models of elegance and efficiency. They emphasize adaptability, using local materials and simple physics to achieve the goal. They work in harmony with the environment rather than trying to overwhelm it with pure power. The challenge and the incredible opportunity for Martian colonization lies not in choosing one approach over the other, but in synthesizing them. How do we take the timeless principles of ancient ingenuity, the low-energy processes, the adaptability, the deep material knowledge, and encode them into our advanced robotic systems? Imagine a future where a swarm of smaller, lightweight autonomous robots is deployed on Mars. Instead of one massive, energy-hungry drill, these smaller units could work collaboratively using a modernized version of fire setting. They might use focused solar mirrors to heat specific rock sections, then apply a precise spray of water electrolyzed from the Martian soil to cool it and cause fracturing. They would be programmed with the geological wisdom of the ancient Romans, but executed with the precision and autonomy of 21st century artificial intelligence. This hybrid approach would allow us to build sustainably, using largely local resources and minimal energy from Earth, creating a true marriage between the wisdom of our past and the technology of our future. This brings us to our first major source of inspiration, a civilization renowned not just for its surface-level grandeur, but for its profound mastery of the world below, ancient Rome. While the Romans built magnificent aqueducts and colosseums that reached for the heavens, they also invested immense skill and labor in constructing vast, complex worlds beneath their feet. Their subterranean achievements, particularly the hypogeums and catacombs, offer a stunning blueprint for how to create functional, stable, and enduring underground spaces, exactly the kind of multi-use environments we would need on Mars. Let's step into one of these spaces. A Roman hypogeum carved deep into the soft volcanic tuff rock that is common around Rome was far more than just a simple cellar or tomb. These were intricate, multi-level complexes that served a dazzling array of purposes. Some were private family burial chambers, adorned with beautiful frescoes and stucco work, creating a dignified resting place that honored the dead. Others functioned as secure storage for grain, olive oil, and wine, leveraging the Earth's natural ability to maintain a cool, constant temperature to preserve precious resources. Some even served as clandestine meeting places for early Christians or other groups seeking privacy away from the eyes of the state. This versatility is a critical lesson. A single underground space does not have to be dedicated to just one function. A Martian habitat would need to be just as multifunctional, combining living quarters, agricultural areas, research labs, and social spaces, all within a protected subterranean network. The true genius of Roman underground engineering, however, lies not in the spaces themselves, but in how they were built to last. These were not crude, hastily dug holes. Archaeologists have uncovered evidence of meticulous planning that rivals any modern construction project. Before a single pick struck the stone, Roman engineers would have carefully surveyed the rock face, identifying the most stable strata to work with. The tunnels and chambers were excavated with precise, deliberate alignment, their shapes often rounded or arched to naturally distribute the immense weight of the Earth above them, a principle that is a cornerstone of modern structural engineering. In areas where the rock was less stable, they employed clever support structures, using built-up pillars and arches made from the same tough rock to prevent collapses and ensure the space remained safe for centuries. Perhaps most impressively, they understood the absolute necessity of airflow. Many hypogeums feature sophisticated passive ventilation systems, using a series of carefully placed vertical shafts known as luminaria. These shafts did double duty. They allowed faint channels of light to penetrate the darkness, but more importantly, they created a stack effect where warmer, stale air would rise and escape out the top while drawing in fresher, cooler air from lower openings. This natural circulation was vital for preventing the buildup of toxic gases, humidity, and stagnation, making these deep spaces not just stable, but genuinely habitable for extended periods. Now consider the geology of Mars. Orbital surveys and rover missions have revealed that vast regions of the planet are covered in basalt, a volcanic rock not entirely dissimilar from the tuff the Romans mastered. While harder, it shares that same igneous origin. The principles the Romans developed for working with volcanic rock, understanding its fracture points, its compressive strength, and how to shape it for stability are directly transferable. We wouldn't be using hand picks. We'd likely use robotic excavators equipped with advanced cutting tools. But those robots could be programmed with algorithms based on Roman excavation patterns, following those time-tested arched shapes and reinforcement strategies to ensure the tunnels they carve into the Martian bedrock are inherently sound from the moment they are created. The Roman Hypogeum stands as a powerful testament to the fact that with careful planning and a deep respect for the material you are working with, it is entirely possible to build a world beneath the world, a lesson we are only now rediscovering as we look toward our future on another planet. While the Romans demonstrated how to carve stable, multi-purpose chambers, another ancient civilization took the concept of underground living to an entirely different scale, creating not just isolated structures but entire hidden metropolises. Journey with me to the stunning, otherworldly landscape of Cappadocia in central Turkey. Above ground, the region is famous for its fairy chimneys, tall, cone-shaped rock formations that seem plucked from a fantasy novel. But the true marvel lies hidden deep below the surface. Here, ancient engineers, likely beginning with the Phrygians thousands of years ago and expanded later by early Christians, carved out breathtaking subterranean cities, with the most famous being Derinkuyu, a labyrinthine world that could shelter up to 20,000 people along with their livestock and supplies. The sheer ambition of Derinkuyu is staggering. This wasn't a simple refuge for a few families. It was a fully equipped, vertically organized city designed for long-term habitation during times of invasion. As you descend through its narrow, sloping passageways, you pass by a complete ecosystem of rooms, stables for animals on the upper levels, living quarters with stone benches and beds carved directly from the rock, cellars for storing massive clay pots of wine and oil, communal kitchens with cleverly designed hearths that funneled smoke through hidden vents to avoid detection from the surface, and even dedicated spaces for religious worship, education, and winemaking. This level of specialized zoning reveals a sophisticated understanding of community needs, planning for every aspect of daily life to continue normally, even while sealed off from the world above. The engineering solutions employed are what truly capture the imagination of modern space planners. The entire city was a masterclass in passive defense and resource efficiency. The entranceways were cleverly camouflaged, often hidden in the courtyards of surface dwellings. Once inside, the inhabitants could protect themselves by rolling massive, millstone-shaped doors across key corridors. These giant stone discs, sometimes weighing over half a ton, could be rolled into place from the inside, effectively sealing off entire sections of the city from attackers. This modular approach to security, the ability to isolate and protect specific zones, is a critical concept for a Martian habitat, where a breach in one section due to a meteoroid strike or pressure failure must not doom the entire colony. But perhaps the most brilliant feat of all was solving the problem of air. How do you provide fresh oxygen and remove carbon dioxide for thousands of people living deep underground for months at a time? The answer lay in a sophisticated, entirely passive ventilation system built around a central, vertical shaft that ran from the deepest chamber all the way to the surface. This acted as a natural chimney. The difference in temperature between the cool underground city and the warmer surface air created a constant convection current. Stale, warm air would rise and escape through the top of this shaft, while fresh, cool air was drawn in through hundreds of smaller, carefully placed ventilation conduits that were often disguised as simple water wells on the surface. This elegant, low-tech solution maintained a constant supply of breathable air without any need for powered fans or filters, a monumental achievement in environmental control. This is the profound lesson Cappadocia offers for Mars. It shows us that a subsurface settlement cannot be just a series of connected tunnels. It must be a holistically designed environment where every element, security, atmosphere, water, waste, and social structure, is integrated from the very beginning. The builders of Derinkuyu didn't fight their geology, they collaborated with it. They understood the properties of the soft volcanic tuff, knowing exactly how to carve it to create stable ceilings, and how to use its natural insulating properties to maintain a constant, comfortable temperature year-round. Their city was not an imposition on the landscape but an extension of it, a symbiotic relationship between human ingenuity and the natural world. For Martian architects, this philosophy is paramount. Instead of seeing the Martian regolith and rock as an obstacle to be blasted through, we must learn to see it as a partner, a resource that provides natural radiation shielding, thermal stability, and the very raw materials from which we can build our new home. The blueprints for a thriving, self-sufficient, and resilient underground community aren't something we need to invent from scratch. They were perfected centuries ago, waiting for us in the silent, stone corridors of Cappadocia. Moving from the vast, hidden cities of Cappadocia, we find another profound lesson in ancient engineering, this time not deep within the earth, but nestled spectacularly within its walls. High on the sun-drenched cliffs of the American Southwest, the ancestral Puebloans created some of the most iconic and enduring architecture in human history. Their stunning cliff dwellings, like the magnificent Cliff Palace at Mesa Verde, represent a masterclass in building with the environment, a philosophy that could be the key to creating habitats on Mars that feel less like sterile bunkers and more like a natural extension of the landscape itself. The construction of these dwellings was an act of profound observation and patience. The Puebloans did not quarry stone and haul it to a building site. Instead, they sought out natural alcoves and overhangs that had been weathered into the canyon walls over millennia by wind and water. They then built their multi-story homes directly into these ready-made sandstone shelters, using hand-shaped blocks cut from the very rock they were building against. This method provided immediate and formidable advantages. The massive cliff face above acted as a giant, permanent roof, shielding the community from harsh sun, torrential rain, and winter snow. The natural rock provided exceptional insulation, keeping the dwellings cool in the scorching summer heat and retaining warmth during cold desert nights. Their position high on the cliff made them incredibly defensible, with access often limited to a series of small hand and toe holds or retractable ladders that could be pulled up in times of danger. But the true sophistication of their design lay in their understanding of solar dynamics. The ancestral Puebloans were meticulous astronomers and engineers. They oriented their dwellings to maximize the benefits of passive solar heating. In the winter, when the sun travels lower across the sky, its rays would penetrate deep into the alcoves, warming the stone floors and walls, which would then radiate heat throughout the night. In the summer, with the sun higher overhead, the massive rocky overhang would cast a cooling shadow over the entire village, creating a comfortable microclimate. They managed water with equal ingenuity, channeling precious rainfall from the mesa tops through carefully constructed canals and cisterns, ensuring a sustainable supply in an arid land. Every aspect of their design was a response to their immediate environment, a symbiotic relationship that allowed them to thrive for centuries with a minimal ecological footprint. This holistic approach to habitation offers a powerful blueprint for Mars. The red planet is not a blank slate, it is a world sculpted by its own unique geology and climate. Just as the Puebloans sought out protective alcoves, Martian colonists will likely target pre-existing geological features, most notably the vast networks of lava tubes that snake beneath the surface. These natural tunnels, formed by ancient volcanic activity, are ready-made caverns that offer superb protection from radiation and micrometeorites. The challenge won't be to build a structure from the ground up, but to adapt and reinforce these natural formations, much like the Puebloans built within their sandstone alcoves. The Puebloan philosophy extends to energy and resource use as well. Their reliance on passive solar principles is directly applicable to a world where energy will be a precious commodity. Martian habitats could be designed within south-facing openings of lava tubes or cliffs to capture the weaker Martian sunlight for natural heating, significantly reducing the load on mechanical life support systems. Their water management strategies inspire methods for extracting and conserving every molecule of water from the Martian soil and atmosphere. Most importantly, their example teaches us that the most sustainable and resilient design is one that doesn't fight the local environment but learns from it and leverages its inherent advantages. A Martian colony built in this spirit wouldn't be an alien imposition on the landscape. It would be a community that feels as though it belongs there, carved from the same rust-colored rock and harmonizing with the rhythms of its new world, a testament to a wisdom both ancient and urgently futuristic. So if the ancestral Puebloans teach us to build with the landscape, then Mars itself may have already provided the most spectacular building sites of all, offering a head start that could shave decades off our colonization timeline. Scattered across the volcanic plains of Mars are countless ancient lava tubes, enormous, cavernous tunnels left behind by rivers of molten rock that flowed beneath the surface billions of years ago. As the outer layer of the lava flow cooled and solidified into a roof, the still molten interior continued to drain away, leaving behind a hollow, tubular void. On Earth, similar tubes in places like Hawaii or Iceland are impressive, but often relatively small. On Mars, however, with its lower gravity and different volcanic chemistry, these structures achieve truly monumental proportions. Orbital imagery has identified cave entrances and skylights, places where the roof has partially collapsed, that reveal tubes estimated to be over 100 meters across, large enough to comfortably contain a wide city street and rows of multi-story buildings with plenty of room overhead. These aren't just empty holes in the ground, they are pristine, prefabricated shelters gifted to us by Martian geology. Their value for colonization cannot be overstated. A lava tube's solid rock roof, which can be tens of meters thick, provides near-total protection from the two most persistent dangers on the surface: solar radiation and micrometeorite impacts. Inside these tubes, the temperature remains remarkably stable, avoiding the wild 300-degree swings experienced on the surface outside, which would drastically reduce the energy needed to heat or cool a habitat. They are, in essence, the perfect natural foundations for a subsurface city, offering a level of protection we could only achieve on the surface with immense effort and enormous quantities of imported materials. The challenge, of course, is that these tubes are natural formations, not engineered spaces. Their walls might be fractured, their floors uneven, and their structural integrity unknown. This is where the visionary work of scientists like Dr. Penny Boston comes into play. As the former director of the NASA Astrobiology Institute, she has long championed the idea of using these lava tubes as the cornerstone of Martian settlement. Her proposals involve sending advanced robotic scouts ahead of human crews. These robots would be far more than simple rovers. They would be sophisticated mapping and construction drones equipped with ground-penetrating radar, LiDAR scanners, and 3D imaging systems. They would descend into these dark, uncharted passages to create exquisitely detailed digital models, identifying stable sections, potential weak points, and the best routes for connecting multiple tubes into a larger, networked habitat. Once mapped, the next phase would be stabilization and modification, and this is where ancient wisdom re-enters the picture. We wouldn't be starting from scratch. We can look to countless examples from history where humans encountered natural caves and expertly expanded them for their own use. The techniques used to widen, reinforce, and ventilate natural caverns, whether in Cappadocia or in the cliff dwellings of Mesa Verde, provide a proven playbook. Robotic workers could be programmed to emulate these methods, using local materials like Martian regolith and basalt to 3D print supportive arches and seal cracks, much like ancient builders used stone and mortar. They could create internal structures that slot perfectly into the natural contours of the tube, maximizing space and strength while minimizing the amount of actual excavation needed. This approach represents a powerful synergy, a true collaboration between the raw, natural architecture provided by the planet and the refined, adaptive ingenuity of human technology, a partnership that could dramatically accelerate our ability to establish a permanent, safe, and sustainable foothold on a new world. Now we arrive at one of the most critical and life-sustaining challenges of living underground, a problem that ancient engineers solved with breathtaking elegance: the very air we breathe. Sealing ourselves away from the harsh Martian surface means we must become masters of our own atmosphere, and history offers a masterclass in how to do this without consuming vast amounts of precious energy. The ancient world is filled with ingenious examples of passive ventilation, systems that moved air using nothing but the immutable laws of physics. In the Persian Qanats, builders incorporated slender, vertical shafts not only for excavation but also as ingenious wind catchers. These towers, rising above the desert floor, were designed to capture the slightest breeze, funneling it down into the tunnels below. The moving air would push stale, humid air out through other openings, creating a continuous, gentle exchange that prevented mold growth and kept the underground workplaces fresh for the diggers, all without a single fan or motor. Similarly, in the deep, labyrinthine tombs of Egypt's Valley of the Kings, architects faced a different but related problem: how to prevent the buildup of moisture and toxic gases in sealed, sacred spaces intended to last for eternity. Their solution was often a dual-entry system. While the main entrance might be grand and obvious, a smaller, more discreet secondary shaft was frequently incorporated. This wasn't an escape route, it was a sophisticated air duct. The difference in temperature between the sun-baked desert surface and the cool, deep chambers underground created a natural convection current. Hot air would rise and escape through the secondary shaft, pulling cooler air in through the main entrance, ensuring a subtle but constant circulation that helped preserve the elaborate paintings and artifacts from the damaging effects of stagnant, humid air for millennia. These passive systems share a brilliant common principle. They work with the environment, not against it. They leverage natural forces, wind pressure, temperature differentials, and gravity to do the work that we today assign to power-hungry machinery. For a Martian colony, where every watt of electricity is a precious resource painstakingly generated by distant solar panels or a small nuclear reactor, this low-tech philosophy is not just interesting, it is absolutely essential. A habitat's life support system will be its most energy-intensive component, constantly scrubbing carbon dioxide from the air, managing humidity, and replenishing oxygen. If we can offload even a fraction of that burden onto passive, ancient-inspired ventilation, we dramatically increase the colony's overall efficiency and resilience. The central question, then, is how we translate these Earth-bound principles to the radically different conditions on Mars. The Martian atmosphere is vanishingly thin, with less than 1% of the pressure of Earth's, and its composition is almost entirely carbon dioxide. This changes the game for passive ventilation, as the forces of wind pressure and convection we rely on here are so much weaker, but they are not absent. The challenge for modern aerospace engineers is to scale the ancient designs to work in this new context. This might involve designing much larger wind-catching funnels to capture the thin Martian winds, which can still be surprisingly forceful. It could mean using the significant day-night temperature swings to our advantage, creating ventilation shafts with materials that expand and contract to pump air, or designing systems that exploit the difference in temperature between sun-facing and shaded sides of a habitat. The goal wouldn't be to replace the complex active life support systems, but to create a hybrid model. Imagine a Martian habitat where sophisticated machinery handles the precise, delicate task of air composition, while a network of carefully engineered passive shafts, inspired by 3,000-year-old Persian designs, handles the bulk movement of air, reducing the constant energy drain and providing a silent, fail-safe backup. It's a perfect fusion, the timeless wisdom of the ancients providing the robust, elegant backbone for our most advanced survival technology. This principle of using what the land provides is perhaps the most powerful lesson ancient builders can teach us about surviving on another world. They didn't have global supply chains or freighters delivering materials from across an ocean. Their entire architectural philosophy was born from a deep, intimate relationship with the local environment. They became masters of their immediate geology, whether it was the soft volcanic tuff of Cappadocia, the resilient limestone of Egyptian tombs, or the hard, precise granite of the Incas. Each material presented its own challenges and opportunities, and ancient engineers developed specific, brilliant techniques to work with them, not against them. The Inca stonemasons, for instance, achieved a level of precision that still baffles modern engineers. They would painstakingly shape massive blocks of irregular granite using nothing harder than stone hammers and bronze tools, carefully carving each one to interlock perfectly with its neighbors. The result was a wall without mortar where you cannot slip a piece of paper between the stones, a structure so flexible and well-balanced that it could withstand the violent tremors of earthquakes that would level modern concrete buildings. This was more than just construction. It was a form of three-dimensional puzzle solving that respected the inherent properties of the stone. This ancient mindset of hyper-local resourcefulness is the exact opposite of how we typically approach large projects today, but it is the only approach that makes sense for Mars. The cost of launching just 1 kilogram of material from Earth into orbit is astronomical, running into the tens of thousands of dollars. Transporting entire shiploads of steel girders, bags of concrete, or prefabricated wall panels is simply not feasible. Instead, we must look at the Martian surface itself as our quarry and our hardware store. The red planet is not a barren wasteland. It is rich in raw building materials. Its soil, known as regolith, is a dusty, fine-grained blend of basaltic rock, iron oxides, and other minerals. Beneath that, the bedrock is largely basalt, the same volcanic rock that ancient builders from Hawaii to India learned to shape and utilize. The challenge isn't a lack of materials, but a question of how to process and use them effectively with minimal energy and imported equipment. This is where ancient techniques and futuristic technology converge in the most exciting ways. One of the most promising methods is regolith sintering, a process that uses focused heat, either from microwaves or concentrated solar energy, to fuse the dusty Martian soil into a solid, ceramic-like brick without the need for water or binders. It's a high-tech version of an ancient practice, firing clay bricks in a kiln, but using the sun itself as the furnace. Another approach takes direct inspiration from ancient compaction methods, like the rammed earth techniques used for thousands of years in China and the Middle East. On Mars, autonomous robots could gather regolith, mix it with a small percentage of a binding polymer that might be synthesized on site, and then compress it with immense force into incredibly dense, strong building blocks. This process would create structures with phenomenal thermal mass, helping to regulate the habitat's temperature, just as ancient rammed earth walls do in desert climates on Earth. The most futuristic vision, however, is large-scale 3D printing using regolith as the ink. Imagine massive robotic arms or swarms of smaller drones extruding a paste of processed Martian soil to slowly build up walls, arches, and domes layer by layer. But the underlying design principles of those structures wouldn't be purely futuristic. They would be deeply ancient. The algorithms guiding these printers would be programmed to create shapes that have been proven for millennia. The Roman arch, which distributes weight outward to sturdy piers, the Inca-like interlocking blocks that provide flexibility, or the corbelled vaults used in Mycenaean tombs, where each successive layer of stone cantilevers slightly inward until the roof is closed. These forms are not just aesthetically pleasing, they are mathematically optimal for stability and strength, especially in an environment where you cannot afford a single structural failure. By combining the raw material of Mars with the time-tested architectural wisdom of Earth, we can create habitats that are not only safe and sustainable, but also inherently resilient, honoring the resourceful spirit of the ancient builders who first mastered the art of making a home from the land itself. We have explored the monumental engineering challenges of carving out a safe haven beneath the Martian surface, from stabilizing tunnels to managing the very air we breathe. But all the structural integrity in the world means little if the minds and spirits of the people living within those walls begin to fracture. The most profound challenge of subsurface living may not be technological, but human. It is a psychological frontier, and once again, our ancient predecessors left us a detailed map for navigating it. The builders of the vast underground cities in Cappadocia understood something that modern architects are only now fully appreciating. A successful habitat is not defined by its walls, but by its ability to nurture the human experience within them. They knew that survival meant more than just air, water, and food. It required light, community, beauty, and a profound sense of connection to stave off the creeping dread of isolation and confinement. Step inside one of these ancient subterranean metropolises, and you immediately notice the thoughtful touches designed to combat the psychological weight of the earth above. Yes, there were defensive stone doors and intricate ventilation shafts, but there were also carefully carved light wells, sometimes called luminaria, that reached all the way to the surface. These weren't just functional air vents, they were conduits for the sun, casting shifting beams of natural light deep into the communal squares and living areas, creating a tangible connection to the outside world and the rhythm of the day. This simple feature provided a vital circadian cue, helping to regulate sleep patterns and moods, a function we now know is critical for mental health. The cities were also meticulously zoned, with dedicated areas for social gathering, churches, wineries, and large open spaces where the community could come together. The walls of these spaces were often adorned with vibrant frescoes, intricate carvings, and symbolic artwork, transforming cold, functional stone into a place that felt decorated, personal, and truly lived in. This was not a grim, dark bunker. It was a home designed to foster normalcy, purpose, and well-being even in the most extraordinary of circumstances. This ancient wisdom is powerfully validated by modern research into extreme environments. Studies of crews on long-duration submarine missions, scientists overwintering in Antarctic research stations, and astronauts on the International Space Station all point to the same critical factors for psychological resilience. Prolonged confinement, sensory monotony, and separation from nature and loved ones can lead to a condition often called expedition fatigue, characterized by depression, irritability, sleep disorders, and interpersonal conflict. What mitigates these effects? The very things the Cappadocians intuitively built into their cities: access to natural light or its close equivalent, private spaces for retreat alongside vibrant communal areas for social bonding, and an environment that includes color, texture, and personal mementos. Modern habitats in these environments prioritize large, shared dining tables for communal meals, walls painted in warm colors instead of sterile white, and individual quarters that astronauts can personalize with photos and items from home. They schedule regular virtual contact with family and mandate communal activities and exercise, all to reinforce a sense of normalcy and connection. For a Martian colony, these lessons are not optional amenities. They are as vital to the mission's success as the oxygen supply. A habitat that feels like a sterile, gray, industrial facility will wear down the spirit, no matter how technologically advanced it is. The design must be human-centric from the very beginning. This means architects and psychologists working hand in hand with engineers. It means incorporating full-spectrum LED lighting that can simulate the daily and seasonal cycles of sunlight on Earth, helping to regulate hormones and sleep. It means designing large, shared atriums or greenhouses, not just for food production, but for the profound psychological benefit of tending living plants and being surrounded by greenery, a concept known as biophilic design. It means ensuring every colonist has a viewport or a high-resolution screen linked to an external camera, providing a visual connection to their new world, a reminder of the grandeur of the mission they are on. Most importantly, it means creating spaces that are not just for living, but for living well: workshops for hobbies, gyms for physical health, quiet libraries for contemplation, and social halls for celebration. The goal is to create an environment where people don't feel like they are trapped in a hole in the ground, but where they are proud members of a thriving community, building a new chapter of human history. By weaving together the intuitive design of ancient underground builders with the precise findings of modern psychology, we can ensure that our first Martian cities are not just shelters that keep people alive, but true homes that allow the human spirit to flourish. So we arrive at a fascinating crossroads, where the patient, handcrafted wisdom of the past must find a new home within the sleek, autonomous bodies of our future. The construction of Martian subsurface cities will be a task of such immense scale and complexity that it simply cannot be accomplished by human hands alone, at least not in the beginning. The risks are too great, the environment too unforgiving. This is a job for robots, but if we simply send our most powerful, modern tunnel boring machines, we might be making a critical mistake, prioritizing raw power over the subtle, accumulated intelligence of millennia. The real breakthrough won't come from choosing between ancient techniques and modern robotics, but from orchestrating a perfect marriage between the two, creating a new generation of machines that don't just dig, but that dig with a kind of inherited wisdom. Think of it this way: a massive, contemporary tunnel boring machine is a marvel of pure force. It is designed to chew through rock with relentless industrial efficiency, its rotating cutter head grinding forward in a continuous, powerful assault. It operates on a principle of overwhelming the problem, but this approach requires an enormous amount of energy, generates intense vibration, and can sometimes cause unexpected stress fractures in the surrounding rock, leading to instability. Now contrast that with the method of an ancient Roman miner using fire setting. Their process was slow, deliberate, and deeply observant. They studied the rock, applied a precise thermal shock to fracture it along its natural fault lines, and then carefully removed the debris. It was a conversation with the material, not a monologue of force. This ancient miner possessed something the modern machine lacks: a heuristic understanding of geology, a feel for the work that prevented collapses and preserved the integrity of the tunnel. The challenge, then, is to endow our Martian robots with this very feel. We must move from pre-programmed instructions to adaptive, intelligent algorithms that can perceive and respond to their environment in real time. This means outfitting autonomous excavators with a suite of sophisticated sensors, LiDAR for creating millimeter-accurate 3D maps of the excavation face, thermal cameras to monitor heat stress in the rock, and acoustic sensors that can listen for the subtle creaks and groans that signal potential instability, much like an ancient miner would listen to the sounds of the mountain. Their programming would be a digital translation of ancient best practices. Instead of a single, relentless forward push, an autonomous digger might be coded to emulate the layer-by-layer, gradual approach of a medieval miner working a coal seam. It would excavate in small, controlled increments, constantly scanning the newly exposed surface, analyzing the rock type and structure, and then pausing to apply reinforcement, perhaps by 3D printing a supportive arch or injecting a rock-hardening resin before proceeding just a little further. This is the essence of the fusion, using high-tech tools to execute low-tech, time-tested principles. The robot becomes the physical embodiment of centuries of hard-won human experience. It doesn't just dig a hole, it carefully sculpts a stable structure, its every movement informed by a vast digital library of geological knowledge and historical construction techniques. The potential for efficiency and safety is staggering. These machines could work around the clock in shifts that no human crew could endure, in conditions that would be instantly lethal to us, all while making thousands of tiny, data-driven decisions per second that collectively ensure the habitat they are building is inherently sound. They wouldn't just be construction equipment, they would be partners, extensions of our own ingenuity, carrying the collective wisdom of every ancient tunneler who ever carefully tapped a rock face to test its strength into the silent, red dust of a new world. This fusion of past and future isn't just theoretical, it's happening right now, in some of the most otherworldly landscapes our own planet has to offer. NASA's ambitious basalt and subsea research programs are essentially dress rehearsals for Martian exploration, conducted here on Earth in carefully chosen volcanic analogues that mirror the conditions we expect to find on the Red Planet. The BASALT project, which stands for Biologic Analog Science associated with lava terrains, has turned the barren, black lava fields of Hawaii and Idaho into a stand-in for Mars. Scientists and engineers don bulky, simulated spacesuits and traverse this harsh terrain, testing everything from new geological sampling protocols to advanced communication systems that must cope with the same time delays they would experience between Earth and Mars. Every rock they examine, every sample they collect, is a test run for the real thing, a meticulous process of working out the kinks in our approach to exploring an alien world millions of miles away. But it's the Subsea project, the systematic underwater biogeochemical science and exploration analog, that truly dives into the subsurface question. This program sends teams to the ocean floor near underwater volcanoes, like the La'ihi Seamount off the coast of Hawaii. The deep ocean is a fantastic proxy for the subsurface environments of other planets. It's an extreme, high-pressure, isolated environment where access is difficult and every move must be meticulously planned. Here, researchers operate remote-controlled vehicles not unlike the future robots that will one day venture into Martian lava tubes, practicing how to map unseen terrain, collect sterile samples, and make real-time scientific decisions based on limited data feeds. They are literally writing the playbook for how we will conduct science in the dark, confined, and potentially life-bearing recesses of another world. A fascinating element of this research is the deliberate re-examination of historical techniques. Take the Roman method of using water to suppress dust during excavation, a simple yet effective solution to a problem that would be exponentially worse on Mars. Martian regolith is not just dust, it's a fine, abrasive, and electrostatically charged powder that could clog machinery, damage sensitive instruments, and pose a serious health risk to astronauts if inhaled. NASA researchers are actively studying how a modernized version of this ancient practice could work. Instead of buckets of water, which are far too precious to waste on Mars, they are investigating the use of misting systems that employ minimal amounts of electrolyzed water, perhaps created by extracting hydrogen and oxygen from the Martian soil itself. This approach perfectly encapsulates the hybrid philosophy. A low-tech InSight water controls dust reimagined through a high-tech, resource-conscious lens. The ultimate goal of all this painstaking fieldwork is validation. It's one thing to design a perfect tool on a computer or test it in a sterile lab. It's entirely another to see how it performs when covered in gritty volcanic dust, handled by gloves that limit dexterity, or operated under the stressful conditions of a simulated mission. These analog missions are where ambitious concepts collide with gritty reality, forcing engineers to adapt and improve their designs. They prove that the strategies we're developing, which so often involve blending historical wisdom with cutting-edge technology, aren't just interesting ideas. They are practical, executable plans that bring us tangibly closer to turning the dream of a subsurface Martian city into an achievable reality. This work stands as a powerful testament to a simple truth. Sometimes the most futuristic vision requires us to take a long, thoughtful look back. This relentless focus on resource efficiency born from ancient necessity is perhaps the single most valuable economic lesson we can apply to the monumental ledger of Martian colonization. Every decision made by those ancient builders was filtered through a harsh reality of scarcity. There were no global supply chains, no emergency shipments of steel from a neighboring continent. If you needed a tunnel, you had to dig it with the people, tools, and materials immediately at hand. This constraint wasn't a limitation. It was the mother of breathtaking innovation, forcing the development of methods that achieved maximum results with a minimum of inputs. This philosophy of frugal ingenuity, of doing more with less, is not just a historical curiosity. It is the absolute cornerstone of any feasible economic model for settling another world. The financial gravity of space travel is the most powerful force any mission architect must contend with. Current estimates suggest it costs roughly $10,000 to launch a single kilogram of payload into Earth's orbit, and the price to send that same kilogram on a months-long journey to the surface of Mars is exponentially higher. This brutal math transforms every piece of equipment, every spare part, and every sack of concrete into a budgetary nightmare. Sending a massive, heavy tunnel boring machine designed for terrestrial mining could easily consume the entire payload capacity of multiple launch vehicles, representing an investment of billions before a single gram of Martian soil is even moved. This is where the ancient approach becomes not just attractive but economically imperative. Instead of focusing on what we can bring, we must shift our strategy to what we can do with what is already there. Envision the very first human landing party on Mars. Their initial habitat might not be a grand, pre-built palace delivered from Earth, but something far more humble and ancient in its spirit, a small, carefully excavated burrow dug using lightweight, multi-purpose tools. The first crews could employ a modernized version of the simple pick and shovel, perhaps electrically powered, modular tools that can be reassembled for different tasks. to carve out a small, reinforced living space directly into the side of a Martian cliff or the wall of a lava tube. This manual, small-scale excavation would serve a dual purpose. Primarily, it provides immediate, life-saving shelter using tools that are lightweight, reliable, and easy to repair. But secondly, and just as importantly, it generates the very first local resource, excavated regolith. This material wouldn't be waste, it would be the feedstock for the colony's first manufacturing efforts. Using a portable sintering unit or a compact 3D printer brought from Earth, the crew could begin processing this spoil into solid bricks, floor tiles, or even structural elements to gradually expand their initial foothold, turning the act of digging directly into the act of building. This bootstrapping approach fundamentally changes the economic equation. It means the initial missions don't have to pay the exorbitant cost of launching every single brick and beam. Instead, they launch a small, versatile industrial kit, a seed factory capable of using Martian resources to fabricate what is needed on site, a concept known as in situ resource utilization, or ISRU. The ancient Egyptians didn't import limestone from across an ocean to build the pyramids. They quarried it from the Giza plateau itself. The Inca didn't have mortar shipped in. They mastered the art of fitting local stone together with impossible precision. This principle of hyperlocality is the key to unlocking an affordable presence on Mars. The goal is to minimize Earth-dependent supply chains as rapidly as possible, creating a self-sustaining industrial ecosystem that can grow from that initial seed. The economic lesson from the past is clear. True wealth and sustainability on a new frontier come not from what you bring with you, but from your ability to unlock the potential of what you find. This journey to Mars is about far more than mere survival. It represents the next great chapter in the human story, and the habitats we build there will be more than just life support systems. They will become the vessels for our culture, the first outposts of a truly multi-planetary civilization. As we look to the future, we have a profound opportunity, and perhaps even a responsibility, to look to our past, to weave the rich tapestry of human history into the very fabric of these new settlements. This isn't about nostalgia, it's about identity. It's about ensuring that as we stretch out into the cosmos, we carry with us the collective wisdom, artistry, and spirit of all those who came before us, honoring the diverse cultures that first mastered the art of living within the Earth. Imagine walking through a central plaza in a Martian habitat and seeing not sterile, metallic walls, but arches and vaults inspired by the grand hypogeums of ancient Rome, their shapes echoing a 2,000-year-old understanding of stability and beauty. Picture communal gathering spaces designed around the same principles of social zoning found in the underground cities of Cappadocia, fostering the same sense of close-knit community and shared purpose that allowed those societies to thrive under pressure. The walls themselves could become canvases, not with generic decorations, but with artistic motifs and narratives drawn from the breathtaking frescoes of sites like the Ajanta caves in India, where ancient artists used mineral pigments to tell elaborate stories of life, philosophy, and spirituality on stone surfaces deep underground. These would not be mere replicas, they would be a new form of cultural dialogue, a way of connecting the first Martians to the long human tradition of creating meaning and beauty in subterranean spaces. This conscious integration of heritage does something vital for the human psyche. It creates a powerful sense of continuity. For colonists living millions of miles from home, surrounded by an alien and inhospitable environment, these familiar cultural touchstones would provide a deep psychological anchor, a tangible link to the world and the history they left behind. It transforms a sterile habitat into a place that feels genuinely human, rich with stories and significance. It answers a fundamental need to belong, not just to a new Martian society, but to the entire, sweeping narrative of humanity. This approach also presents a fascinating challenge. How do we decide which elements of our vast and varied heritage to bring with us? Do we create a kind of greatest hits compilation of global architectural styles, or do we allow specific cultural groups to establish colonies that reflect their own unique traditions? This process forces us to confront what we value most, to decide what aspects of Earth's cultural identity are essential enough to be granted a place in our future among the stars. Furthermore, this endeavor raises even larger questions about cultural preservation and transmission in an entirely new setting. The artifacts we bring, the designs we choose, the stories we tell, these will form the primary curriculum for the first generations of children born on Mars. Their understanding of Earth's history and the breadth of human achievement will be fundamentally shaped by the environment we build for them. This makes the architects and planners of these early habitats not just engineers, but curators of human culture and inadvertent teachers for a new branch of our civilization. The choices they make will echo for centuries, influencing Martian art, social norms, and even language. By thoughtfully incorporating the legacy of ancient tunneling societies, we do more than just build sturdy homes. We lay the foundation for a Martian culture that is deeply rooted, resilient, and proudly connected to the long, innovative, and beautiful story of life on Earth. Of course, every great undertaking carries inherent risks, and carving out a home beneath the surface of an alien world is no exception. The ancient tunnelers we've been admiring were not immune to catastrophe. They worked in a constant, intimate dance with danger, facing the ever-present threats of sudden collapse, unexpected flooding, or the silent, creeping peril of bad air. Their successes were hard-won, paid for with lessons learned from failure, and it is from these very failures that we can extract a priceless manual for survival on Mars. The risks they faced have direct, terrifying analogues in the Martian environment. A structural failure in a tunnel on Earth might trap a handful of miners. A similar failure on Mars, millions of miles from any hope of rescue, could doom an entire colony. The loose, unstable Martian regolith surrounding a habitat could shift unpredictably, much like the treacherous sands that plagued Egyptian tomb builders, requiring ingenious solutions to lock it in place. And a failure in the artificial life support system, the lungs of the colony, would be as fatal as the black damp or choke damp that claimed the lives of countless medieval miners. What saved these ancient engineers was not just bravery, but a deeply ingrained methodology of precaution born from observation and experience. They understood that rushing was the enemy of safety. One of the most universal principles across centuries and cultures was the practice of gradual, incremental excavation. Medieval miners in Europe, for instance, developed a meticulous process for digging their narrow shafts. They would only advance a short distance, perhaps the length of their body, before stopping to reinforce the freshly dug section with a sturdy wooden frame called a timber set. This dig a little, shore up a little approach ensured that the unstable earth above was never left unsupported for long, dramatically reducing the chance of a catastrophic collapse that could bury them alive. This patient, step-by-step philosophy stands in stark contrast to the dig first, ask questions later approach of a modern tunnel boring machine. And it is precisely this cautious pacing that we must encode into our robotic Martian workforce. This ancient strategy of incremental progress offers a powerful template for how we could approach stabilizing tunnels on Mars. Instead of sending a single, colossal machine to carve out massive caverns in one go, we might deploy smaller, modular robots that work in a carefully orchestrated sequence. The first wave of bots would be the pioneers, excavating just a few meters of tunnel at a time. Immediately behind them, a second team of robotic sappers would move in, their task not to dig but to build. Using a process called sintering, fusing the surrounding Martian dust into a solid, ceramic-like material using focused heat or microwaves, they would instantly line and reinforce the new excavation, creating a continuous, strong shell before any more digging occurs. This creates a safe, sealed tube behind the workface at all times, a secure retreat for both machines and any future human supervisors. It's a high-tech, automated echo of the medieval miner carefully hammering his timber set into place before allowing his partner to take another swing with the pick. Beyond collapses, the ancients also mastered the art of managing water, a threat that might seem irrelevant on the dry surface of Mars but becomes critical when working underground. On Earth, tunnelers often encountered hidden aquifers or flooding, and their solution was not to fight the water head-on, but to guide it away. The builders of the Peruvian Huachuca region, for instance, incorporated clever, subtle drainage channels into their underground structures to divert seepage and prevent erosion that could undermine foundations. On Mars, the liquid threat is different but equally dangerous. A breach in a water recycling tank or a humidity control system could release liquid into the habitat or, even worse, into the surrounding regolith. Martian soil, rich in perchlorate salts, could become a corrosive, unstable slurry if saturated, potentially weakening the structural integrity of the entire tunnel network. Here, the ancient wisdom of drainage and diversion becomes vital. Martian habitat designs could incorporate passive, gravity-fed drainage systems inspired by these old-world techniques. Floors could be gently sloped toward central collection, grates that funnel any accidental spills or condensate not into the soil, but into emergency containment vessels where the water can be recovered and purified. This turns a potential disaster into a recoverable incident. Furthermore, the ancient practice of selecting sites with natural drainage building on a slight rise or in well-draining soil informs how we choose the location for our Martian subterranean cities. We would prioritize lava tubes or excavation sites with a natural gradient, ensuring that any potential fluid leak has a designated, safe path away from critical infrastructure, guided by the same simple, reliable force of gravity that ancient engineers relied upon. By studying how our ancestors turned potential catastrophes into manageable problems, we arm ourselves with a toolkit of strategies that are both elegantly simple and profoundly effective, allowing us to anticipate challenges on Mars that we might not yet even have imagined. This fascinating fusion of past and future isn't happening in a vacuum. It's being actively forged in a new kind of laboratory, one where the dust of ancient ruins meets the clean room precision of aerospace engineering. We are witnessing the birth of a truly revolutionary collaboration, a partnership that would have been unthinkable just a few decades ago. In universities, research centers, and even at NASA facilities, archaeologists who specialize in ancient technology are now sitting side by side with aerospace engineers who are designing missions for Mars. These are not just casual conversations, they are deep, interdisciplinary exchanges where a knowledge of Roman concrete recipes is considered just as valuable as a proficiency in computational fluid dynamics. The synergy is powerful because each field brings a critical and complementary piece of the puzzle to the table. The archaeologists and historians offer something that no computer model can yet provide: the invaluable data of time. They are the keepers of long-term performance reviews. When an aerospace engineer designs a structure, they can run simulations and stress tests, but their data only extends for a few years at best. An archaeologist can walk them through a tunnel in Cappadocia that has remained standing and stable for over a millennium, point to the specific construction techniques that made that possible, and explain how the materials have behaved under centuries of environmental stress. They provide real-world case studies of durability, showing us which ancient solutions succeeded, which ones failed, and most importantly, why. This deep understanding of material behavior over vast timescales is pure gold for an engineer trying to design a habitat that must survive on Mars for generations without any possibility of replacement. In return, the engineers bring the tools to quantify, model, and scale this ancient wisdom. They can take the qualitative observations of an archaeologist. The Romans used this specific arch shape because it felt more stable, and translate it into a precise digital model. Using finite element analysis, they can simulate the exact load distribution of that Roman arch, subject it to simulated Martian seismic activity, and calculate its factor of safety to a degree of accuracy its original builders could never have imagined. They can use modern material science to analyze the molecular structure of ancient hardened mortars, and then use robotic fabrication to create new, optimized versions using Martian regolith. The engineer's contribution is to take a brilliant, time-tested idea and refine it, test it, and prepare it for execution in an extraterrestrial environment. The fruits of these partnerships are already emerging as breathtaking hybrid designs. We're seeing conceptual drawings for Martian habitats that feature the passive ventilation shafts of a Persian Qanat, but are made from 3D printed regolith composites whose recipes were informed by chemical analysis of Inca stonework. We see plans for autonomous digging robots whose excavation algorithms are based on the gradual, layer-by-layer, dig and reinforce patterns used by medieval miners, ensuring maximum stability with minimal energy expenditure. These aren't just futuristic concepts, they are historically grounded, deeply thoughtful designs that represent the best of both worlds. They have the elegant, time-proven simplicity of ancient engineering and the precision, power, and scalability of modern technology. Fostering more of these cross-field exchanges is not just beneficial, it is essential for accelerating our progress. The challenge is breaking down the traditional silos that separate academic disciplines. This requires creating dedicated spaces for this collaboration to flourish, establishing joint research positions between university archaeology departments and aerospace companies, funding grants that explicitly require interdisciplinary teams, and organizing workshops where a specialist in Egyptian tomb architecture can present their findings directly to a team designing radiation shielding. Mars, the goal is to build a common language, a shared vocabulary where a term like structural integrity means the same thing to someone studying a 2,000-year-old vault as it does to someone designing one for another world. By intentionally building these bridges between the past and the future, we unlock a vast, untapped reservoir of human knowledge, ensuring that the next giant leap for mankind is taken with the collective wisdom of all our history firmly supporting it. This profound shift in perspective from conquering a frontier to nurturing a new home brings us to perhaps the most crucial dimension of this entire endeavor, the ethical framework that must guide our actions. As we prepare to break ground on another world, we are presented with a rare and powerful opportunity to learn from the deepest and most enduring relationships between humans and their environment, those forged by indigenous cultures across our own planet. Many of the ancient tunneling and building techniques we've been exploring were not developed in a vacuum. They were born from a worldview that saw the land not as a resource to be extracted, but as a relative to be respected, a living system of which they were an inseparable part. This is a fundamentally different starting point than the colonial, conquer and settle model that has dominated so much of human history, and it offers a vital blueprint for how we might approach Mars not as invaders but as humble guests. Consider the ancestral Puebloans of the American Southwest, whose breathtaking cliff dwellings we admired earlier. Their sophisticated architecture was not an act of domination over the landscape, it was an act of integration. They chose building sites that maximized passive solar heating and natural protection. They used local materials with minimal processing, and they designed their communities to have a light touch on the surrounding ecosystem. Their entire philosophy was built around living in balance, ensuring that their actions would not degrade the environment that sustained them for generations to come. This long-term thinking, this intergenerational responsibility, is the exact ethical compass we need for Mars. We cannot afford to see the red planet as a blank slate for reckless experimentation or a mere backup plan for a depleted Earth. We must see it as a fragile, unique world that we have a responsibility to care for from the very first moment we arrive. This means establishing clear, forward-thinking guidelines before a single shovel of regolith is turned. First and foremost, we must commit to the principle of planetary protection in its fullest sense, not just preventing our microbes from contaminating Mars, but also preventing our industry from irrevocably scarring it. Our mining and excavation for building materials should be conducted with the same care and reverence that an indigenous artisan might show in quarrying a special stone for a ceremonial object. We should prioritize non-invasive methods, target areas of minimal scientific interest, and strive to leave the vast majority of the Martian landscape pristine and untouched for future scientific discovery, and perhaps one day its own inherent natural value. This approach stands in stark contrast to historical patterns of resource extraction on Earth, which have often prioritized short-term profit over long-term planetary health. Furthermore, this ethical framework must be inclusive and equitable from its inception. The knowledge we are drawing upon is a global human heritage belonging to no single nation or corporation. Therefore, the process of establishing these guidelines cannot be dominated by the handful of countries and private entities currently leading the space race. It requires a global conversation that actively includes and elevates the voices of indigenous leaders, ethicists, and representatives from developing nations. We must ask difficult questions together. Who does Mars belong to? How do we ensure that the benefits of space exploration and colonization are shared by all of humanity, not just a privileged few? How do we prevent the replication of Earth's historical injustices on a new planetary scale? The answers will shape the kind of civilization we become out among the stars. By consciously choosing to learn from cultures that built for sustainability and community, rather than exploitation and exclusion, we have the chance to write a new and better chapter for humanity, one that honors the wisdom of our shared past while responsibly pioneering an unimaginable future. Given the breakneck pace of current technological advancement and the sheer volume of resources being dedicated to interplanetary travel, the vision of a functioning Martian city by the middle of this century is rapidly shifting from science fiction into a tangible, working blueprint. This ambitious timeline, often championed by high-profile visionaries like Elon Musk and the engineers at SpaceX, isn't just a publicity stunt. It's a goal that is actively shaping research and development in aerospace, robotics, and construction. The first Martian settlers won't be arriving to a gleaming city of glass spires under vast domes. They will be pioneers entering a world still under construction, a subsurface network of interconnected modules and tunnels that will slowly, over years, evolve into the first true extraterrestrial metropolis. This city will be a living entity, growing and adapting, and its initial form will be almost entirely underground, a direct and necessary response to the planet's lethal surface conditions. So, what might a typical day look like for an early resident of this underground city, perhaps around the year 2050? Your morning wouldn't begin with a view of a sunrise over a red horizon, but with the gentle, gradual brightening of full-spectrum LED panels embedded in your ceiling, programmed to simulate the dawn light of a specific location on Earth, perhaps the Arizona desert or the French countryside, to help regulate your circadian rhythm. Your compact private quarters, while ergonomically designed and personalized with digital photos and mementos, would be part of a larger, vaulted chamber carved directly into the Martian bedrock, its walls lined with a ceramic-like glaze created from sintered regolith that provides both radiation shielding and a pleasing, warm texture. The air might carry a faint, clean, metallic scent, a constant reminder of the intricate, constantly humming life support systems that recycle every molecule of oxygen and water. After a breakfast synthesized from vertically farmed algae and lab-cultured proteins, your commute to work wouldn't involve a car or a train, but a short walk or a ride on a slow-moving automated trolley through a wide, arched tunnel. These main thoroughfares would be bustling arteries of activity, connecting different districts of the subterranean complex. One tunnel might lead to the agricultural domes, vast, pressurized caverns where the red glow of full-spectrum grow lights bathes rows of genetically modified crops in an eternal artificial summer, their photosynthesis providing a significant portion of the colony's oxygen. Another tunnel branch might lead to the central research labs, where geologists analyze the latest core samples drilled from deep underground, and biologists study extremophiles for clues on how life might persist on Mars. The air in these tunnels would be filled with the quiet hum of machinery and the faint, constant breeze of the passive ventilation system, a modernized version of the wind-catching towers from ancient Persia, using subtle pressure differences to keep the air fresh. The social and psychological heart of the city would be the main commons, a large, central plaza excavated to feel open and airy despite being buried under meters of rock. This space would be designed explicitly to combat the potential for isolation and claustrophobia, drawing direct inspiration from the communal squares of Cappadocia's underground cities. Here, beneath a high, vaulted ceiling that projects a realistic, real-time video feed of the Martian sky above, colonists would gather for communal meals, celebrations, and meetings. Children might play in designated areas under the soft, simulated sunlight, while others tend to small gardens of earth plants, their greenery providing an invaluable psychological boost. This would be more than just a cafeteria. It would be the town square, the living room, and the park for the entire community, a critical space for maintaining morale and a sense of shared identity millions of miles from home. Ultimately, life in this first Martian city would be a study in contrasts, unimaginably high technology employed to achieve the most basic human necessities, all within an architectural framework that is, at its core, ancient. The colonists would be some of the most highly trained scientists and engineers in human history, yet their daily survival would depend on principles of underground living perfected by Roman architects and Persian water engineers millennia ago. They would be surrounded by the silent, desolate beauty of an alien world, yet they would experience it primarily through camera feeds and the windows of their surface rovers. This unique existence would forge a new kind of human culture, one deeply rooted in the collective knowledge of Earth's past while being fundamentally shaped by the extreme demands of a future on Mars. The timeline is aggressive, but it is this very urgency that is finally giving the brilliant, hard-won engineering lessons of our ancestors the serious, practical application they have always deserved. While the surface of Mars appears utterly alien with its rust-colored deserts and thin, pink sky, a closer examination of its fundamental geology and climate reveals striking parallels to specific, extreme environments right here on Earth, places where ancient human civilizations not only survived but thrived by mastering the art of subsurface construction. This unexpected kinship between our home planet and our future destination provides a critical bridge, offering a practical, real-world playbook for how we might approach building a new home on the Red Planet. The cold, dry, and largely volcanic character of Mars finds its closest earthly cousins in the dramatic lava fields of Iceland, the wind-scoured deserts of Iran, and the high-altitude, arid plateaus of the Andes. These terrestrial analogues are not just scientific curiosities, they are living museums of ancient engineering genius, where millennia-old solutions to problems of heat, cold, rock stability, and water scarcity are etched into the very landscape. Consider the vast volcanic plains of Iceland, a land forged by fire and ice. Here, the bedrock is primarily basalt, a dark, fine-grained igneous rock formed from rapidly cooling lava. The very same type of rock that dominates the Martian surface, as confirmed by our rovers and orbital surveys. The early settlers of Iceland faced a brutal environment, punishing winters, limited fertile soil, and an abundance of this tough volcanic rock. Their response was to turn this challenge into their greatest asset. They learned to quarry and shape the basalt, splitting it along its natural columnar joints to build sturdy homes and protective walls. But their most ingenious adaptation was going underground, constructing turf-covered longhouses where thick walls of earth and stone provided superb insulation against the Arctic cold, maintaining a stable, livable temperature inside while blizzards raged outside. This direct, practical understanding of how to use local volcanic rock for shelter and thermal regulation is a priceless dataset for Martian architects. The techniques Icelanders developed for working with basaltic rock, how to fracture it, shape it, and structure it for maximum strength and insulation, are directly transferable to processing Martian regolith and bedrock. Hundreds of miles away, in the arid and sun-baked landscapes of Iran, ancient Persian engineers faced a different but equally harsh set of conditions: extreme heat, minimal rainfall, and deep, porous aquifers that made surface water a rarity. Their legendary response was the Qanat system, a masterpiece of hydrological engineering that we explored earlier. But the relevance for Mars extends beyond just water management. It encompasses the entire philosophy of working in a dry, brittle environment. The rock in these desert regions is often fragile and prone to collapse, much like the loose, unconsolidated regolith on Mars. The Mukani, the master builders of the Qanats, developed an intimate knowledge of how to reinforce their tunnels in such unstable material, using ceramic rings and compacted earth to create a durable lining that prevented cave-ins. This expertise in stabilizing tunnels in dry, granular, and non-cohesive soil is perhaps one of the most immediately applicable ancient skills for Martian construction, where the #1 priority will be preventing a catastrophic collapse in the powdery, unpredictable regolith. This comparative analysis does more than just provide a list of handy tips. It offers a fundamental shift in perspective. It allows us to stop seeing Mars as a completely unknown and hostile abstraction, and to start seeing it as a familiar type of geological and climatic puzzle, one for which humanity has already developed a diverse and sophisticated toolkit. By rigorously studying these terrestrial analogues, we can move from theoretical models to proven practices. We can test ancient Persian tunnel reinforcement techniques in simulated Martian regolith here on Earth. We can analyze the thermal properties of Icelandic turf insulated basalt walls to inform the design of passive heating and cooling systems for a Martian habitat. We can study how the ancestral Puebloans of the American Southwest managed to conserve and utilize every single drop of water in an environment of profound scarcity, a skill that will be paramount for a colony that cannot afford to waste a single molecule. This process of planetary comparison essentially gives us a cheat sheet, a way to leapfrog centuries of trial and error by standing on the shoulders of the ancient engineers who already did the hard work. It bridges the intimidating gap between terrestrial experience and extraterrestrial application, transforming the monumental challenge of building on Mars from a blank slate problem into a process of intelligent adaptation. We are not starting from zero. We are starting from a foundation of millennia of hard-won wisdom, inherited from those who first learned to coax life and stability from the most unforgiving corners of our own world. Their legacy is the closest thing we have to a field guide for becoming a multi-planetary species. This crucial fusion of past and future wisdom is now finding its way into the very classrooms and training facilities where the next generation of Martian architects are being trained. It's no longer enough for an aerospace engineer to be a master of computational models and advanced materials science. The most forward-thinking universities and space agencies are now insisting they also become students of history. A new educational movement is taking root, one that deliberately integrates the study of ancient engineering principles into the standard curriculum for planetary scientists and habitat designers. Imagine a course at a leading technical institute where the semester's reading list includes not only the latest NASA technical reports on regolith properties, but also translated manuscripts from Roman architects like Vitruvius and detailed archaeological surveys of Andean irrigation systems. This isn't about nostalgia, it's about building a more complete and resilient intellectual toolkit. The goal is to produce engineers who can look at a problem like how to stabilize a tunnel in loose Martian soil and draw solutions from a library of knowledge that spans thousands of years, not just the last few decades. They learn to see the elegant simplicity of a Persian qanat's ventilation shaft as another valid data point alongside the output of a complex fluid dynamic simulation, understanding that both have critical roles to play in designing for another world. The most effective programs are moving beyond theoretical study and embracing a truly hands-on experiential learning model. Students might find themselves spending a weekend not in a computer lab, but at a dedicated field site, participating in a workshop run by expert masons and traditional builders. Here, they trade their keyboards for a set of replica Roman tools, the pick, the drag, the wooden shovel, and are tasked with the humbling challenge of excavating and reinforcing a small section of tunnel using only these simple instruments and the principles of corbelling and arch construction. The immediate physical feedback is transformative. They feel the strain in their muscles as they learn the most efficient angle to swing a pick to fracture rock with minimal effort. They gain an intuitive, tactile understanding of soil mechanics and stability as they carefully shore up their excavation with wooden beams, experiencing firsthand the consequences of moving too quickly or ignoring the subtle warning signs of an impending collapse. This direct physical engagement with ancient methods builds a deep-seated intuition that no digital simulation can fully replicate. It teaches restraint, observation, and a profound respect for the material they are working with, lessons that will be invaluable when they are remotely supervising autonomous robots on Mars, allowing them to recognize potential problems in the data feeds because they once felt a similar shift in the Earth with their own hands. This holistic educational approach is fundamentally about fostering a new kind of problem-solving mindset, one that values adaptability and resourcefulness as highly as computational power. By grounding students in both the timeless principles of the past and the cutting-edge tools of the future, we are creating a generation of innovators who are bilingual in the language of technology and the language of the Earth. They are learning that sometimes the most advanced solution is not the most complex one, but the one that most elegantly meets the need with the resources available. The ultimate challenge and the great opportunity lies in creating a living, evolving repository for this blended knowledge. We need to move beyond isolated university courses and build a sustained, global effort to catalog, study, and experimentally test these ancient techniques in modern and extraterrestrial contexts. This could take the form of international research consortia linking archaeology departments with engineering schools, or digital archives where 3D scans of ancient structures are available for engineers to run virtual stress tests upon. The goal is to ensure this precious knowledge is not a passing academic trend, but a permanent and continually growing core of our approach to space exploration, constantly refined and adapted for the unprecedented challenges that await us. This powerful narrative, weaving together the distant past and the far future, possesses a unique ability to capture the public's imagination in a way that pure technical specifications or futuristic concepts sometimes struggle to achieve. There's something deeply resonant, almost poetic, about seeing a documentary filmmaker stand in the silent, stone corridors of a 2,000-year-old underground city, and then cut to an animation of a similar structure being carved by lasers into the side of a Martian cliff. This connection transforms the audacious dream of interplanetary colonization from a cold, abstract engineering problem into a profoundly human story, one about resilience, ingenuity, and the timeless urge to build a safe home against all odds. Media outlets and documentary producers have been quick to recognize the appeal of this angle, crafting narratives that frame our journey to Mars not as a rejection of Earth's history, but as a celebration of it. This storytelling approach demystifies the science, grounding these incredible endeavors in a legacy we can all understand and feel a part of, which in turn builds a broader, more durable base of public support that transcends political or national boundaries. The impact of this positive and thoughtful media representation extends far beyond generating mere excitement. It serves as a critical engine for inspiration, actively shaping the ambitions of the next generation. When a young person watches a show that explains how the ventilation shafts in a Persian Qanat work, and then immediately shows how a NASA engineer is adapting that principle for a Martian habitat, it does more than just teach a fact. It creates a powerful aha moment, a tangible link between the mysteries of history class and the possibilities of science class. It makes the field of aerospace engineering feel accessible and creative, showing that it isn't just about crunching numbers on a computer screen, but about solving human problems with a vast and diverse toolkit that includes art, history, and anthropology. This can be the spark that convinces a curious student to pursue a career in STEM, not because they feel they should, but because they see a thrilling and meaningful path where they can literally help build the future by understanding the past. The challenge and the incredible opportunity lies in continuing to refine how we tell these stories to a global, digitally native audience. The classic documentary format will always have its place, but the future of this communication is interactive, immersive, and personalized. Imagine a virtual reality experience that allows you to don a headset and literally step into the shoes of both an ancient Roman architect surveying a tunnel site and a 21st century engineer reviewing a robotic LiDAR scan of a Martian lava tube, toggling between the two perspectives to see the principles they share. Envision educational video games where players are tasked with managing the resources and crew of a fledgling Martian colony, forcing them to make difficult decisions about energy allocation, food production, and structural integrity, with in-game tutorials based on real historical case studies of ancient societies that faced similar constraints. These immersive formats transform passive viewers into active participants, creating a much deeper and more personal understanding of the complex trade-offs involved in such a monumental undertaking. Furthermore, the narrative must be inclusive and multifaceted, avoiding a simplistic ancient wisdom saves the day trope. The best stories will also explore the complexities and the ethical dilemmas, inviting the audience to think critically. A compelling documentary might follow the collaboration between archaeologists and engineers, not shying away from the moments of friction when a 1,000-year-old technique clashes with modern safety protocols or material limitations. It could feature debates among ethicists, historians, and indigenous leaders about the responsibilities we carry to other worlds, giving the audience access to the full, rich conversation surrounding space exploration. By presenting these endeavors in their full complexity, we foster a more sophisticated and engaged public discourse, moving beyond spectacle and toward a genuine, global conversation about what we want our future among the stars to look like and whose stories we choose to take with us. The staggering economics of space travel have long been the single greatest barrier to becoming an interplanetary species, a wall of financial impossibility that has kept human dreams of Mars firmly in the realm of science fiction. But that wall is now beginning to crumble, not under the force of a radical new invention, but from a surprising source of inspiration: the frugal, resource-efficient philosophies of ancient engineers. The realization that we might not need to launch every single nut, bolt, and brick from Earth, but can instead use the planet itself as our construction warehouse, has fundamentally reshaped the financial calculus of Martian colonization. This potential for dramatic cost savings and enhanced mission sustainability has triggered a powerful and decisive response from the two primary forces capable of funding such an endeavor: national space agencies and the burgeoning private space industry, both of whom are now pouring significant investment into research that bridges the gap between the ancient and the extraterrestrial. For government entities like NASA and the European Space Agency, the interest is driven by a dual mandate of exploration and fiscal responsibility to their taxpayers. Their missions are planned over decades and budgeted with immense scrutiny. Every dollar saved on one project can be redirected to another. The prospect of using in situ resource utilization, or ISRU, to dramatically reduce the mass, and therefore the eye-watering cost of payloads launched from Earth, is not just attractive, it is a game-changing strategic imperative. Instead of funding the development of a single, monolithic, and impossibly expensive tunneling machine, these agencies are now financing a diverse portfolio of smaller, smarter technologies. Grants are flowing to university labs studying the material properties of ancient Roman concrete, seeking to reverse engineer its legendary durability using Martian soil simulants. Contracts are being awarded to robotics firms that are programming autonomous diggers with algorithms based on the gradual, stabilization-first techniques of medieval miners. This isn't just scientific curiosity, it is a calculated investment in risk mitigation, proving that we can reliably extract water from regolith, manufacture building materials on site, and construct stable habitats using local resources directly reduces the number of things that can go catastrophically wrong on a mission millions of miles from help. It transforms a Mars mission from a fragile, all-or-nothing endeavor into a more resilient, adaptable, and ultimately achievable venture. The private sector, led by visionary companies like SpaceX and Blue Origin, is motivated by a different but equally powerful set of economic incentives. Their business models are built on scalability and the long-term potential for profitability concepts that are impossible if every mission requires the budget of a small nation. For a company like SpaceX, the entire architecture of its Starship vehicle is predicated on reusability and refueling using Martian resources. The economic incentive to make ISRU work is existential. It is the key to unlocking a self-sustaining transportation system between planets. Consequently, private investment is aggressively targeting the technologies that will make this a reality. We are seeing venture capital funds dedicated solely to space resources, backing startups that are developing everything from compact regolith sintering ovens to autonomous drilling rigs. The private sector's agility allows it to act as a rapid testing ground for these ancient-inspired ideas, funding small-scale prototypes and demonstrations that can fail fast, iterate quickly, and prove their value outside the more rigid timelines of government bureaucracy. Their goal is to create a new industrial revolution off-world, and they recognize that the most viable foundation for that revolution is a return to the hyper-local, resource-efficient principles that built civilizations on Earth. So what economic incentives could further accelerate this fascinating convergence? One powerful driver would be the establishment of clear property rights and international treaties that grant companies ownership or exclusive rights to the resources they extract and the structures they build on Mars. This would create a tangible asset class, encouraging massive private investment in the development of extraction and construction technologies. Another incentive lies in the burgeoning field of space tourism and commercial research. The company that first masters the art of building safe, comfortable, and psychologically supportive subsurface habitats on Mars won't just be building for scientists. They will be designing the first extraterrestrial hotels and research campuses for corporate clients. The entity that can offer a turnkey solution for establishing a presence on Mars, providing the power, life support, and infrastructure, will unlock a trillion-dollar market. This potential for a first-mover advantage in an entirely new industry is a siren call for investors. One that ensures the fusion of ancient wisdom and modern technology will continue to receive the funding it needs to move from the drawing board to the red sands of Mars. This global tapestry of underground innovation reveals a profound truth. The drive to carve safety and community from the Earth is a universal human impulse, one that transcends borders, eras, and cultures. From the vast subterranean metropolises of Cappadocia to the intricate water tunnels of Persia, from the defensible cliff dwellings of the ancestral Puebloans to the deep, ceremonial labyrinths of ancient Malta, every continent holds examples of societies that look downward to survive and to thrive. This isn't a history owned by any single nation. It is a shared inheritance, a global catalogue of solutions to the universal problems of shelter, security, and resource management. The study of these techniques has, by its very nature, always been an international effort, requiring archaeologists, historians, and engineers from around the world to collaborate, share findings, and piece together a collective understanding of our species' underground past. This collaborative spirit, built on mutual respect for diverse cultural achievements, provides the perfect blueprint for how we should approach our future on Mars. As we begin to sift through this global catalogue of ancient wisdom, selecting and adapting techniques for an extraterrestrial environment, we are presented with a rare and beautiful opportunity. The first Martian city won't be built solely with American robotics, European life support systems, or Chinese launch vehicles. Its underlying architectural soul will be a fusion of ideas from every corner of our home planet. The passive ventilation might draw from Persian wind catchers, the structural arches from Roman engineering, the use of local materials from Inca stonemasonry, and the communal zoning from the underground cities of Turkey. This means the very walls of a Martian habitat will physically embody a celebration of human cultural diversity. They will stand as a monument not to the triumph of one culture, but to the collective genius of all humanity, a permanent testament to the fact that we arrived on Mars not as competing nations, but as a unified species carrying the best of our entire history with us. This inherently inclusive foundation forces us to confront a critical question with profound implications. How do we ensure that this spirit of global collaboration shapes not just the hardware of the colony, but the very fabric of its society? The goal must be to avoid replicating the colonial models of Earth's past, where exploration often meant exploitation and the imposition of a single cultural viewpoint. Instead, we must consciously architect a Martian society that is equitable and representative from its inception. This begins with the mission architecture itself, ensuring that the crews, the scientists, and the engineers involved represent a true cross-section of humanity, bringing a multitude of perspectives, problem-solving styles, and cultural values to the table. It continues in the design phase, where input should be actively sought from a global community of thinkers, including indigenous leaders whose cultures possess deep knowledge of sustainable living and long-term stewardship. The societal structures established in those early, formative years will set a precedent for centuries to come. Will the governance of a Martian colony be inclusive and participatory, drawing on democratic principles from various Earth cultures to create a new, hybrid model of decision-making? How will the educational systems teach children about their heritage, a curriculum that only highlights the scientific achievements of Western nations would be a tragic failure? Instead, it should tell the full story, explaining how the water recycling system is inspired by ancient Arabian practices, how the agricultural domes use principles developed by Andean farmers, and how the social harmony of the community is informed by philosophies from across Asia and Africa. This creates a population that understands its profound debt to all of Earth's peoples, fostering a global citizenship that could become a model for a more peaceful and cooperative future back on our home planet. By intentionally weaving this rich tapestry of cultural acknowledgement into daily life, we can build a Martian society that is resilient, innovative, and proudly unified in its magnificent diversity. From the Qanats of Persia to the lava tubes of Mars, this incredible journey through time and technology reveals a profound and humbling truth. The thread of human ingenuity is unbroken, connecting our most distant past to our most ambitious future in the most unexpected of ways. We've ventured from the hand-carved water channels beneath ancient deserts to the concept of sprawling subterranean cities on another world, and at every step, we've found that the solutions we so desperately need for tomorrow were often perfected centuries, even millennia ago. These ancient tunneling techniques are far more than just historical curiosities or fascinating artifacts in a museum. They represent a deep, hard-won catalog of knowledge on how to live in harmony with our environment, how to use minimal resources for maximum effect, and how to build structures that endure not for decades but for centuries. They are a testament to a different kind of innovation, one born not from limitless power, but from profound constraint and an intimate dialogue with the Earth itself. This legacy offers us something priceless as we stand on the brink of becoming a multi-planetary species, a blueprint for sustainable survival. The challenges of Mars are immense, but they are not entirely unique. They echo the harsh conditions that ancient engineers faced in deserts, on volcanic plains, and in frozen tundras. Their response was not to overwhelm nature with brute force, but to understand it, to adapt to it, and to cleverly leverage its own properties to create safety and stability. This is the exact mindset we must carry with us. It teaches us that our future on other worlds may not be found in the most complex machine we can imagine, but in the most elegant synthesis of old and new, pairing the timeless principles of passive ventilation, local material use, and community-centered design with the precision and power of autonomous robotics and advanced material science. We are not starting from scratch. We are standing on the shoulders of giants, of countless unnamed Mucani, Roman miners, and Puebloan builders whose collective wisdom is our most valuable inheritance. So as we look to the stars, let's carry forward this wisdom. Let's ensure that the first footsteps in Martian dust are guided by a deep respect for the lessons carved in Earth's stone. This is about more than just engineering. It's about continuing a story that began thousands of years ago, a story of resilience, creativity, and the unshakable human drive to create a home, no matter how hostile the environment. We'd love to hear which ancient innovation resonates most with you. Does the sheer scale of Cappadocia's cities capture your imagination? Or is it the elegant simplicity of the Persian Qanat that you find most inspiring for our future? Share your thoughts in the comments below. Let's continue this conversation about how our past is digging the way forward. And if you've enjoyed this journey through the tunnels of time, make sure to subscribe for more explorations where we uncover how the roots of our history are shaping the branches of our future.